let's do an example of using this to calculate the area of a circle. So we've got a circle, let's make it of radius A, and what I'm going to do is I'm going to divide it up into lots of little squares. I'm going to calculate the area of each of those squares and then add them up using integration. So we have here, I can just copy it down from where we had it before, that the individual little pieces have area A r d r d theta. And now what I want to do is to get the total area by summing, which I do with an integration, but I have to integrate on changing r from 0 to a, and also changing theta to go all the way around from 0 to 2 pi. So I'm going to do an r integral from 0 to a, and a theta integral from 0 to 2 pi. And that will sum up all of these little area elements on the surface. You'll note that I've divided this up. I've taken all of the r dependence out the front, and all of the theta dependence is therefore here, and so I can just do those two integrals separately. So in particular, the integral d theta of 1 is theta, and when I put in the limits of 0 and 2 pi, I get 2 pi. And when I do the r integral, I get r squared over 2, and I put in the limits, and I get a squared over 2. And when I then multiply those two together, I find that the 2's cancel, and I get pi a squared, which of course is the correct answer for the surface area of a circle.